Jonas, first of all, for your presentation. Hello, everyone. I want to present to you our research project for the summer, context adaptation for tactical decision-making roundabouts. First, I want to discuss the topics that we talked about in the middle of this presentation. During the mid-race presentation, we talked about this paper, this new paper, Rosario. And for like a quick summary of what Rosario is just a speed advisory framework for roundabouts, and it had two parts. First was occupancy prediction, which is basically if you look at picture, there's defined zones which it took data from all the vehicles and using a transformer it would predict in the future of 5 seconds they'll predict like occupancies in the zone. And then using this data, it would train RL agent, mainly PPO, with the given reward function and give speed advisories to the agent. So what speeds to take in the entrance of roundabouts. And this is a transformer that they used, which is basically 5 different sets of pipelines for each second of predictions. However, for the scope of RIS, we decided not to include results and not to discuss Rosario in the poster, and for several reasons. First was we had problems with the baseline results. So when we took the repository and without changing anything, we ran their trained model, we would get the same results that they had in the paper. But when we didn't take the already packaged model and we decided to retrain it with the same configuration without any changes, it would give different results in each run, and that was because they did some bad things in the testing and training. And for example, they didn't exclude testing from the training set. So another point was we realized that their paper was about the entrance of roundabouts, and they didn't simulate anything in the roundabouts. And this didn't fully align with our project's goals. And the third thing was for the risk posters and presentations, we wanted to have something visual. And since they didn't have simulations, we decided to go with some simple roundabout simulation highway environment. And after this, we could continue working with Rosario, since we spent some time understanding it, and we could maybe use their methodology or something similar. So why did we not focus on highway environment simulation from the beginning? Initially, we had one issue that was they used IDM vehicles for the simulation, which were in roundabout settings didn't perform as a good environment, and they when increasing the number of vehicles, they would often collide. And you don't need to read the contents of the picture, but this is basically a comment from the author of the repository, saying exactly the same thing, that IDM and mobile work mainly on highways, and if you increase the number of vehicles, then on roundabouts and intersections, they would collide. They suggested a fix that you would just ignore collisions with within the environment, but we didn't do that. So after going back to highway environment, we decided to try to fix some issues and continue with working highway environment. So currently what we have is, you can see a different lane roundabouts. And we decided to use, for example, instead of IDM cross vehicle model, and add some behavioral logic, which is not perfect. They still some vehicles are still I guess stopping for not so good reasons, but they no longer collide as they used to. So we decided to use this kind of environment. And yeah. So as for the methodology, since we are talking about context awareness, we have the agent observe limited amount of vehicles on the roundabout, and we want to also use the context of the whole scene. So, sorry, that's the next slide. Sorry. We found a paper in regards to our work, and this paper turned out to be really good for us because what they did was they reviewed all the reward functions and how they shape them and what is the standard of using them in autonomous driving in RL. In one of the paragraphs, for example, we can see the gap which they clearly stated, and I believe they reviewed like I think 40 or so like papers. I don't know exactly. As it says, none of the reviewed papers made modifications to the reward function to incorporate like context awareness. And this is exactly what we wanted to do. So as for the context, we decided to use, for example, decided to use aggressiveness of the environment, which depends on the speeds of the other vehicles and acceleration. We can take different ways to consider which is more important for us. We decided to use density, which is just straightforward the natural, like the number of vehicles over the natural limit of the roundabout. And then we decided to use impatience for the vehicle, which can be derived from like several things, mainly underperformance. And below you can see the impatience is just decaying over time and is adding the underperformance with some P. You can see the patience value here. And this means that if it crosses the underperformance crosses the P value, then we would add, and then over time it decays. To consider the underperformance, there can be like we have these three different ways to calculate. And the first way, for example, would be just to look at the agent itself, and if its speed in the couple like past 5 seconds or something, some window is less than 2 meters per second or some threshold, then we would consider the number of such like seconds as underperformance. We could also look at the difference between the speed between the ego vehicle and other vehicles, and if the speed is different, like more than some small like value. And the right formula is basically same as considering the speed of the vehicle, the mean speed of the vehicle, so other vehicles and ego vehicle to some reference speed. And so we decided to use we decided to define the reward function as the sum of safety, comfort, and efficiency. We defined these three terms as the safety using the time to collision, using the time to, function of time to collision, the efficiency as the speed with respect to the maximum speed and minimum speed, and comfort as basically from the actions the agent takes. If it takes, for example, actions fast, slow, it would get punished more. Since we do high-level decision making, the agent only does these actions. For example, turn left, turn right, go slower, go faster, idle. And K here, for example, is the number of decisions from last opposite action decision. And if K, for example, is 5, so last time we made a left turn was like 5 decisions ago. And if we do a right decision to turn right now, then it would not get as much punished as it would have if it did in close window. And as for the dynamic weights, we tried several different formulas for the safety weights to depend on the density or impatience or aggressiveness. And here C is just the sum of aggressiveness and density divided by 2. And between these different dynamic weight reward functions, we decided to display these three for today. And as a baseline, we looked at different weights for the reward function, and we decided to settle for these two sets of weights, 10, 1, 1, and 10, 3, 1. We should note that we didn't have time to do a quick search to find the optimal weights for the problem, since each training took several days. So yeah, let's talk about first the time limitation. Due to the race deadlines, we had the limitation of the training, and we decided for this to only save on single lane roundabouts. And this was because on single lane roundabouts, the training took 2 days, around 2 days. And for 2 and 3 lane roundabouts, it took 4 and more days. So it would be the fastest to check our formulas on single lane roundabout and report the results. And because of the time limitation and to check actually if the dynamic weights worked, we decided to only train for DQN, and then we would extend to other models and to compare. So on the left, you can see the runs, for example, the context adaptive runs, run trainings, and they all have the converging shape at 500,000 steps. And on the right, yeah, you can see, for example, one of the simulations of the Ego vehicle. And as for the results, here we have 4 different tables, and we have all the, for example, let's consider the topmost table. We have the F4 formula, which is only using impatience. It has 0.9 in success metric and the highest out of all 5. And as for the safety, it's the lower, the highest as well, so it's better than others. As for efficiency, it's a bit lower than others, and comparing to second baseline, we have 37% of crash rate drop. We can also compare different splits of the environment. For example, light conservative, aggressive, also optimizable and non-optimizable. These splits we took from Rosaro, this idea, because they defined 2 sets of environments, which was optimizable, non-optimizable, and they defined the non-optimizable as if the vehicle goes full speed, then would it need to stop at all with collide or not? And those are the non-optimizable cases. And you can see the fourth formula has the safety, its other formulas in safety, everything except non-optimizable cases. And as for the last table below, we have the time on entry before the roundabout. And you can see that the first formula actually stays quite some longer time than compared to the base 1 formula. And this is straight from the safety formula we have here. That we use 10 minus 3 times patience. And since the safety weight is negative, the longer it stayed on the ramp, the lower this weight got. And so it stayed longer on the entrance since it got punched less for staying there and looked for the gap traffic. And in the splits of light conservative, light aggressive, and dense conservative and dense aggressive, we have improvements of 20%, 51%, 57%. Light aggressive, no difference. And we can see actually, we have here the different splits in the environments. So here you can see the left side is conservative, the more the point is on the right side, it's more aggressive. These are different environments, these dots, and we have like 500 of them. And on the y-axis, we have from light to dense. And these 5 red plots are for each of the runs. And you can see, for example, that F9 performed better than F4 in the light conservative case, which can be seen from this table, performed slightly better. And you can see that all the models for now struggle with conservative and dense traffic at the same time. And as for the F4, it improves on F1 aggressive dense traffic. So for future work, what we will do is, since we had this limitation of time, we were able to run only limited amount of like formulas and relationships and dependencies in the weights. So we will continue to explore more weight changes, dynamic weights, and analyze their behavior. Also, we would like to train on multiple lane roundabouts, since we were not able to do so for RIS. And in the meantime, while this training takes place, we would like to focus more on the theory as well, because for me personally, I wasn't able to much focus on the theory while the RIS was going, because I wanted to get the results. But after this, this would be easier. And the next goal would be to evaluate on other RL algorithms other than QI. And yeah, this is also, I think it came on my side. Let's see. Good.